Hey, hey! It's been a pretty long while. Well, welcome back. Today, if you're caught up to speed, we're going to be talking about Quilibrium 2.1. And if you're just visiting this channel for the first time, that's weird, but okay, welcome. Just a quick disclaimer, the discussion today is not a solicitation for investment and is not financial advice. The Quill and corresponding wrapped Quill tokens discussed on this broadcast are utility tokens, and Quilibrium Inc. does not endorse or encourage engaging in speculation on the utility token of the network. With that out of the way, let's go ahead and talk about the agenda for today, because this is going to be a pretty long stream. I'm going to go ahead and let you guys know, if you haven't been paying attention to socials or other channels, this is going to be split into a two-parter, in part because, one, enrollment's still in progress, and two, because this deep dive is a very long deep dive. It's going to be rather technical. So I'm going to try my best to keep it relatively quick-paced, because there's a lot of stuff to get through and not much time to do it. And also, on that note, we've got an update to 2.1 coming out. It's currently going through signing as we speak. So, without further ado, let's go ahead and talk about the mission. The mission of Q, of course, is to secure every bit of traffic on the internet, whether it is on Quilibrium, in service of other protocols, or in service of the broader web. Now, we've had many different demonstrations of this, and of course, one of our biggest demonstrations is our flagship product, Quorum. Obviously, there's quite a few people who are using Quorum every day, and they've been keeping track of this, but the first item I wanted to talk about is just the updates that have been coming to Quorum. The team has been hard at work adding more and more features to the web application, and of course, in the coming week after enrollment concludes, we will have Quorum Mobile being released. Alongside that, for those who weren't paying close attention to the news about Quorum Mobile, for those who signed up for the beta, you'll be getting a free Q name service name, and it'll also correspond with the unlock of the Q name service. The Q name service is basically our equivalent to the Ethereum name service. It works a little bit differently. We don't have quite the same, setup in terms of, like, we don't do rentals. We do like just straight up acquisition. You buy a Q name, you have it for life unless you want to sell it. So there's going to be some distinctions, and we're going to walk through that when we launch the Q name service. As our normal pattern has been, we've been doing the broadcasts historically on Sunday nights for me. I think it's Monday morning for a lot of folks in Europe and in Asia, but that's the same pace we're going to keep from here on out. It's going to be the source of weekly updates and the dev streams where we talk about how to build on Q. Yeah, that's basically the summary of all the high-level events outside of the big ones, of course, being 2.1 and some of the upcoming partnership announcements. Now, before people get too carried away, as I said before, we do not announce partnerships or even confirm them if they're speculated. I know some of you have heard some rumors around the grapevine. We don't confirm them until both sides are ready to announce, and we're going to maintain that, which is the same reason why we are happy to announce about ZapMe acquiring BlockChat. We are very supportive and very excited for them as they are going through the transition of being brought on board with ZapMe. They are going to be bringing in BlockChat as ZapChat onto ZapMe in the coming weeks or months. I don't quite know their full timeline at the moment, but it'll be one of the first non-Q Inc. products that is powered by Q that we're very excited to be working with them for, and obviously that is the first of many that we will be discussing. Also, I have my phone locking on me, so I don't have the chat pulled up for Twitch. Give me a sec. It's been a few months. I'm a little rusty. Yeah, that's true. It's not a partnership, but shout out to Bang for getting through many long nights. No kidding. It's definitely been a long ride. It's been many 18 to 20 hour days, and sometimes, God, I think the longest was like 70 hours or so, 70, 72. It was rough, but we're finally here, and the network is now running on 2.1. So what that means for us is going to be the enrollment process, as we've been talking about for a while. I'm going to walk through what that actually looks like and what to expect and how that's going to play out. And then we'll dive into the post enrollment phase stuff. Let me pull this up real quick. Okay, yeah, so some other items real quick. After 2.1 launch has concluded, we're going to be getting into the launch of all the other additional services. Like I said, Quorum Mobile will be out. We're going to have the Q console, Q storage, Q name service, QKMS, and then as time goes on further, we're going to be rolling out F of X, which is our equivalent to AWS Lambda, and also Relational, which is our equivalent to a couple of different services. It's going to be our equivalent to RDS, Amazon Key Spaces, DynamoDB, and Redis. And of course, as subsequent upgrades to the protocol roll out as well, we'll start to bring out some of the more fun stuff like Claru for machine learning and our streaming data primitives that you'll actually get to be previewing as part of Quorum Mobile for phone, video, and streaming content calls. Okay, so let's go ahead and dive into 2.1. I'm going to move some stuff out of the way. Bear with me here. I'm working on kind of a limited device at the moment. It's I'm basically having to manage OBS on the same screen as this stream, so it's going to get a little bit meta here for a moment. But okay. Okay, sorry about that. I don't know what happened, but it automatically started playing a stream, so it started echoing. Okay, cool. Now let's get to talking about 2.1. All right. So this is going to feel a little familiar for people who have seen some of these streams before. But we're going to be going through, for those who are not as familiar with Q2.1, or what it is that we're all doing, I'm going to talk about, yeah, that's not far off. But yeah, anyway, the mission behind Q, as I said, it's to secure every bit of traffic on the internet. And it comes from a realization sourced many years ago, is that, you know, the inevitability of the current state of the internet is that we are under a multi-sided attack, and it is encroaching on our privacy and freedom on the web. And the way that this attack is playing out is through a variety of different actors, whether it's for identity, personal storage, communication, the internet service providers, the internet infrastructure providers, or government. These attacks are coming from all, sometimes even working together, sources. And this isn't just a phenomenon in the United States, as people are finding out, whether they are just posting a meme in the UK, whether they are just growing their company and it gets large enough that it gains popularity in another country. If you get too big outside of the States, well, guess what? You get sold to one of the biggest surveillance supporting regimes in the US. So this phenomenon is something that I've seen the writing on the wall for a long time about, and I've been talking about it for years, and I've been building Quilibrium as a result of this realization for years. And the culmination of this has come out in the form of 2.1. And the reason why we have to build this, it comes down to, you know, when you look at existing products out there, or existing blockchains even, like you're thinking crypto could potentially solve this, right? The problem with crypto is that when you actually take the aggregate sum, you take the entire throughput of all of the chains that are combined, that are actually decentralized. I'm not going to, for a single second, acknowledge chains that are just wrappers for Google Spanner. That doesn't count. If you take actually decentralized chains and you just add the performance together, the actual performance of it is less than the number of transactions per second you would need to provide just iMessage in 2016. In other words, we're just not there. Like the current idea of just put it on the blockchain doesn't work. And the reason is because blockchain has an inherent scaling limit. Now, I've given a few other talks on this, and you can actually find it either on YouTube, where I talk about the alternative thesis of consumer crypto. You can find different times I've mentioned it on various social media. But the idea is simple. Like, blockchain just has an intrinsic bandwidth limit that you cannot scale past without sacrificing decentralization. And so, well, okay, if you can't solve it with crypto as it is, how do you solve it? Well, you do solve it with crypto, but you just have to, oh, shoot, I have this out of order. Fun times. But anyway, the way you solve it is to essentially take the concepts that we've learned from crypto and just kind of tweak it and move things around so that the network is now highly parallelized and also utilizes some of the cutting edge research around zero knowledge proofs and MPC in order to provide private execution at instant finality at global scale. And so the way this plays out has resulted in managed services that we're going to be offering on Q, and also through the core primitives of Quilibrium. We had already been, testing in production, so to speak, some of these things for quite a while, but 2.1 brings a lot. For example, we now have an onion routing layer on the network to provide network level privacy, along with a secure permutation, like a multi-party computation protocol that does secure permutation of traffic in order to provide a mixed net on top of that to provide analytic privacy. We have a confidential compute compiler, or MPC compiler, that turns applications into garbled circuits and enables you to compute data privately. We also have a overall data structure on which all of this is stored, which is an oblivious hypergraph. It is an oblivious data structure that utilizes MPC in order to cooperatively write data to it, yet reveal no content to anybody but the holder of the key that reveals that content. And in addition, we of course have a token primitive that makes it possible for a incentive basis for the network to operate. And so what's coming up with this is the first generation of Q services. Like I said, our S3 compatible API, our Lambda compatible API, KMS, CQL, Redis compatible, RDS compatible. And the whole purpose of this is essentially to take the existing cloud model, as we recently saw this week, where things start breaking down because one data center goes down, and invert it into a decentralized context that never has to go down because it is fully decentralized. And so what is happening right now with our enrollment process is essentially laying the groundwork for all the nodes that are currently on the network to essentially sign up for, here's the shard I want to cover, here's the shard I want to cover, here's all the workers that I have, here's the storage that I have, and it just kind of figures it out based on what resources are available on your machine. And with that, the network is able to essentially load balance all of this in a way that doesn't run into issues around strict global consensus. And I'll dive into how that works in a bit, but that's kind of the gist of it. It enables essentially the entire service offerings of the original Amazon Web Services back when they were just getting started to serve as essentially that kernel that we are planting in order to grow into the massive forest of offerings that is Amazon Web Services today. And so as a consequence, that leads us into what will become the second generation of services: streaming video, confidential machine learning, streaming audio, image store, meta virtualization, and scheduled tasks. So thinking about this in terms of positioning, that kind of puts us in a very unusual place, because as the more decentralized you are, the harder it is to be generalized. And we essentially achieve this in a way that is utilizing the research that has been put into motion for the sake of trying to improve existing protocols. But existing protocols have what is often referred to as ossification. And ossification is the phenomenon that, as a protocol becomes more complex and is used by more and more people, it has this tendency to stagnate in growth because it is much harder to roll out an upgrade. And so by consequence, we came up with a different design that enables greater flexibility in adding new features and allowing individual nodes to offer what they can and move forward. I'm going to go ahead and pop open the chat real quick because my phone once again locked. This is fun. Oh shoot, thank you so much. I didn't realize that, I forgot my my video portion is in the way of some of this. Sorry, in the bottom right corner, there's the logos for Azure, AWS, and Google Cloud. I'll try to notate that as we move through this. But essentially how this plays out in terms of overall benefits is we're solving the needs for Web 2. We don't have to worry about AWS US East 1 being down again. We don't have to worry about senior talent leaving Amazon and suddenly they're lost at sea for hours as they figure out all that institutional knowledge that they essentially lost because they decided to issue a return to office. It is a permissionless protocol. In other words, you can't be deplatformed from the protocol. So, there's a lot of social media companies that were really starting to crop up in the late 2010s. You could agree with them, you can disagree with them, it doesn't matter. When it comes to the concept of freedom of speech, like the idea that, somebody wants to say something and as long as they're not violating any laws, why can't they be allowed to say it? Well, unfortunately, when things are politically inconvenient for larger companies, they tend to pull the plug on you, and that is exactly what happened. And so the phenomenon of Quilibrium is that, it is a permissionless protocol. You can't be deplatformed from the protocol. It's also edgeless. Like there's no need to do this like split architecture between edge services and a primary region. There is no primary region. The other benefits are much more like specific to individual circumstances, but it all kind of encapsulate in user freedom and overall lower price. And then for, of course, the Web3 crowd, which quite a few of you are more in that crowd, there's also the same kind of like corporate concerns that large companies building on Web3 have to care about. In particular, compliance is a big one. There's a lot of retail wallet as a service offerings, and they're not compliant. They're straight up lying. And that day of reckoning is coming soon for them. But using QKMS essentially de-risks their entire problem that they're currently facing. So it's a very attractive platform for those types of service offerings. But one of the things I think is the most important lesson learned, and it's something that I saw in the early days of Ethereum with Solidity. It's something I saw with Solana with their, like, yes, it's Rust, but it's like Rust targeting a really specific runtime with a lot of like really specific libraries that you have to use, and it's just kind of a pain in the ass. The big problem in developing for Web3, I don't know if you just heard the thunder, I've got a thunderstorm going on right now. The big problem for Web3 is that when you're building applications, the languages that you use are often bespoke. And the consequence of that, on top of being bespoke, having like really weird leaky abstractions, it leads to bad code being written, vulnerabilities unexpectedly or unintentionally being introduced, and also doesn't let you use the wealth of software that's been invented for the past decades. And so instead, the language that we support with our built-in compiler is Golang. And so it turns into a very easy thing. You can just use the language that you already know with the wealth of software that already exists and deploy it to the network. But in addition, it also makes all of that difficulty so much easier. You get the advantages of multi-party computation and input privacy for users without actually having to design custom protocols, because the compiler effectively turns it into that custom protocol for you. In addition, of course, there's also the economic benefits and composability benefits of doing decentralized services. And then finally, the big thing for us is that we have privacy at every single layer in which an application interfaces with the network. And so what that ultimately leads to is what I call the end game. The end game being that the future of software is something that we're finding is turning into a measured medium that's billed in terms of usage per hour or usage per day, depending on the provider. And the realistic outcome is that eventually that'll get so granularized that it's, at the request level or even at the bit level. And so when we're looking at the reality of cloud services enveloping the entire web, which they pretty much already have at this point, that wasn't the case back when I started this project, and the fact that privacy is being violated at practically every single level, trying to solve the privacy problem is also solving the cloud restrictions model by simply coming up with the next stage of the internet. And so what a lot of people have said is like the inevitability is that like things will be built at such a granular level. I believe that to be true as well, but the only way you can do that is if you actually have a crypto-styled system for metering everything at that level. And if you're already at that point, then why not take advantage of all the other benefits of privacy and security? And so that's what we've done. So that's the high level of Q. What that actually has led to is the culmination of 2.1. And so, as I said, right now we're currently in the process of the enrollment phase. We've got an update going out that's going to be helping some nodes that have been having difficulty getting set up. There's a lot of different bespoke configurations that we're supporting, and so sometimes bugs fall through the cracks with certain combinations. One of those is the fact that the new worker model has every single node that's propped up, all the workers that you have under that node, they're all running their own pub sub connections and their own streaming services connections. And so by consequence, that can be a real challenge for people who are like running behind a, like a local ISP, like they're running it at home. And so we have support for a proxy mechanism, and that unfortunately had a bug in 2.102. So we have 2.103 coming out that should help resolve that issue. Let me check chat real quick because I am getting frequently disconnected from it. Makes me wonder if the stream is actually still working. Give me a sec. Okay, cool. All right, so please wait for the enrollment to finish. I am not waiting for the enrollment to finish on this stream. I will have another stream on Sunday after the enrollment has completed, and we'll talk about like the outcome from that entire process as well. Okay, so that brings us to the beginnings of the 2.1 deep dive. One thing I want to mention real quick is we've tried to make things a little bit easier for folks. If you haven't run run a node before, like if you haven't built this before, we have an architecture guide that's in the repository that kind of like outlines all the different pieces and how they all communicate. We also have some additional like pointers on where to go in the project to find different things that you might need. And then also we have nice like helpful build scripts to get things up and running. But high level, you will want to have Rust installed. You will want to have Golang 1.24. Technically, if you have like 1.21 or anything newer, it will auto upgrade for you as part of the build system. But that's the version we're targeting is 1.24. And you'll also need a few other utilities. But like I said, we have some helpful install scripts. So if you go into the scripts folder, you'll see, like, for example, we have a full install script to put every dependency that you need for Ubuntu in place. Very similarly, we have the same kind of thing for Mac, but it's in a different set of instructions. So let's go ahead and talk about the structure starting from the node level, and we'll work our way out. So the best way to talk about this is essentially the startup process. So the startup process, as any Golang application, starts at main, and then from there we load the configuration and pull all the different configuration options out, pass it through into the constructors that we have created through just Go wire. If you've ever used dependency injection in any other language, wire is basically like static dependency injection. It's code generated instead of dynamically generated like most languages do. And basically that process goes through wire, sets up all the connections to all the implementations of interfaces, plugs everything in, and essentially gets to the point where we run start. But like I said, this is a multi-process application. So the main master process, which is labeled core 0, runs and then has, if you're using the default configuration, it essentially detects the number of cores that your machine has and will calibrate itself to spawn the appropriate level of workers based on the resources of your system. And then it will spawn the data worker nodes alongside that. Let's dive into the actual start process, which I scrolled past. Go me. There we go. Okay. So when you're actually starting this, the very first thing that begins is essentially global consensus. That is in the way that the network's structured, let me zoom in a little bit because I know that this is probably going to come up really blurry on Twitch. And let me check stream chat again. For that one specific chat, I actually did see it, so yeah, no problem. I know we're close on that. Okay, so awesome. All right. So anyway, we go into the start of global consensus. And so the structure of the network works out essentially at 2 tiers. One of the things I didn't pull up in that keynote, let me, shoot, there's no way to get back to that, is there? Nope, sure isn't. Okay, well that's fine. I'll just sketch it out. Let's see here, Onyx Galadraw, great. Okay, so essentially we have 2 different tiers of consensus. And the first tier is at the global level. The second tier is at the app shard level. And at the global level, we are maintaining a set of 256 values. And I'm not going to make all those boxes because that would be way too much work and it wouldn't even actually have enough room for it anyway. And so essentially those 256 values correspond to, essentially you can think of it as like a compression. Like if you're not familiar with like zero knowledge proofs, you can just think of it as like a compressing function that takes the entire world state of the network and rolls it up into 256 values. Why is this important? Because if you have a super condensed amount of proof information, then the overall data that every single node needs to know, whether it's a light node that's just simply submitting transactions to the network, or an active node that's proving on the network, all you need to know in order to prove anything about the network is to have those 256 points, and they're 74 bytes a piece, so 74 times, if I actually can type things correctly, comes out to roughly 19 kilobytes. So 19 kilobytes of data can prove more like statements of truth than there about things than there are atoms in the universe, is essentially how the math works out too. And so that's a really powerful tool because what it means is that at the global level, you know, you think about chains like Ethereum where they're able to process, you know, what I think their top speed they've ever had was 62 transactions per second. If you only need to manage 256 points of data, in other words, 256 elliptic curve operations at the global level, that means your proofs are really small, really fast, really cheap. And that means that if that data is being distributed quickly, because it's small, cheap, and fast, then you can actually maintain global consensus very easily, and that lets you scale out really, really wide. And so by consequence, even in the initial state of this network for the 2.1 enrollment, in terms of actual logical shards of data that exists on the network, we have literally over 100 million shards of data. But when we're getting at the logical distribution of those shards, we're going to be starting off with roughly 4096, not even roughly, sorry, 4096 shards initially for the network. Now, how does that work out? So when you're thinking about how the data is partitioned on the network at the global level, like I said, there's 256. And then these points essentially correspond to a map that is a compressed, oh shoot, this is all going to be in, there we go. Okay. It essentially compresses into a map that is a series of different values in a tree that roll up to the overall global state. So say that we have this app shard here. Every statement of fact about that singular app shard, those app shards are actually members of a much larger proof or a much larger set of data about the entire app address level itself. And that is expansive to whatever you need because it is a tree structure. We can just keep expanding it out. But the unique nature of the way these proofs work is that it essentially rolls up such that, due to in this case, the tree is actually 64 array instead of binary, but due to the nature of the structure of the tree and the proof system that we use, it actually only requires a single point corresponding to the root commitment point in order to prove any of these individual shards of data, or drill it down further, any of the actual logical shards under that app shard. And so the way that this prover system works is that you have essentially the global consensus that everyone participates in, and then you have the app shard level consensus that a clique of nodes, so to speak, is participating in, and those are what your workers are working on. When they create their given proofs, they're essentially rolling up their little bit of state changes into a singular proof that goes into the overall global proof tree. And then from there, that actually corresponds to the 3 of the individual sectors of the global state. The reason we do this is because it essentially turns into a self-error correcting code distribution. So that way we can ensure that even if an entire shard goes offline, we don't lose any data. And so all that together creates a proof system that can scale out to potentially millions of actual shards instead of just like logical shards running at any given time without impacting global consensus. All right, so getting back into that, that's where we start with this. And so at the global consensus level, you can see it's kind of, it's not quite a God function or God class as you might expect. Like, yes, it's very beefy. Yes, it has a lot of different state being managed, but really what the global consensus engine itself is doing is just plugging in all those values together to actually provide the emergent functionality of global consensus. And so what that actually amounts to is if you're curious about how the consensus mechanism itself works, you can actually just drill into that one specific item. So we have a consensus state machine, and rather than, helps if I can spell, rather than actually try and search for it, I'll just search, or, hunt and peck for it, I could just search for it. So we have the consensus package, the statemachine.go file. It is a very well-commented file with tests wrapped around everything that helps explain how our basic consensus works. So we created a generic consensus engine, like the state machine, and it provides essentially Byzantine fault-tolerant consensus. We actually have other mechanisms that reduce the requirement of less than 1/3 Byzantine failures to a much smaller number through the use of our mixnet. Like, essentially it provides the functionality of avoiding those types of consensus failures, but at its core, like if you just used it as is, it's essentially BFT consensus. And so it'll feel very familiar for people who have ever had to work with BFT consensus engines of any kind. But it's very straightforward. Like, you can actually leisurely walk through it and see the various states of this state machine, how those are handled, what types of messages map to them, and what the transition states are from the events that can be emitted. And so what that essentially amounts to for us is a small number of different states that correspond to sequence of events of the state machine looping pretty much indefinitely as the network runs. And so to talk about that, because there's going to be times where we may need to, for example, like if we have to roll out a protocol upgrade, we may have to care about what point in the overall consensus state that we're in when that actually takes effect. But we can actually inject into any given state that we want with those protocol upgrades. So we don't have to worry about, like, for example, when Ethereum moved from ETH1 to ETH 2.0 with the beacon chain, they had this weird total terminal difficulty that they had to match up to rather than what the block height was of the original chain. We don't have to really worry about any of that because we can plug into the various states of the state machine instead of having to do this weird calculation to make sure that the network actually reaches the state we need it to. So in this case, it's pretty simple. You have a loading state, and that's where it will synchronize with the network. We have the collecting state, where it's collecting the overall data for the consensus round and prepares a proposal. We have the liveness check, which is to basically say, hey, I'm alive, this is what I've collected, I'm just letting you know that I'm alive so everyone else can be aware whether to expect any messages from me for this round. And then there's the actual proving state, which is non-emitting. It's just essentially a state where your node is going through the process of generating a proof, and then the publishing state where it is publishing and potentially waiting for others to publish, the voting state where everybody's going to be voting on proposals who was previously live, and then the finalizing state where the voting decision is made and consensus is reached, which ultimately is acknowledged in the verifying phase. And then it starts all the way back over to collecting. If there's any failures in any of these states from collecting to verifying, it kicks you back into loading and you'll resync with the rest of the network. That's basically it. This tight loop is the consensus engine of the network. Where it's actually, or what it's actually maintaining consensus on, as I said, is the the oblivious hypergraph. And like I illustrated in the Excalibur drawing, it's essentially a system that manages a bunch of trees. But obviously, if it's a hypergraph, why are we dealing with trees? And the answer is because the hypergraph is essentially a CRDT. And so we need to maintain like data that is being put into the various phase sets of the CRDT. And so the hypergraph is a two-phase hypergraph. So there's essentially adds and removes vertexes and hyper edges, and the actual data representation of that would be done through a tree. And also we get the really cool effect of being able to have really concrete tight proofs with very little data having to be communicated by using said tree, because it's a vector commitment tree or a vertical tree. So anyway, all this is to maintain the overall global state. And so when you start it up, you have the worker manager, which starts the background data workers if you're not in archive mode. It has the execution manager, which has the execution engines that need to start, primarily the global one at the global level, makes sense, which manages the actual like prover enrollment, which is what people are going through right now. The event distributor, which I will probably have to defer that to the next stream because the event distributor is kind of complicated. You can think of it as like the essentially the timing chain that runs through the engine, and if there's any misfires on that, bad things can happen. And so it's worth its own talk because it was a source of many painful delays. We also have the global time reel and then the corresponding clock store for the frames of the global time reel. Time reel is essentially that, that engine that is maintaining the order of frames on the network. So if provers disagree on something, how do we like resolve that and get back to consensus? Let's see. We have some basic kickoff stuff around Genesis, which is kind of hacky, but we needed to do it. And then we have our overall pub-sub connectivity for the mesh networking to work out. We have a bunch of different topics that your node will subscribe to. One is, of course, for global consensus if participating, but there's going to be ones that are generally used by all peers, like overall shard consensus, getting any frame publications that are happening, prover messages, peer info messages, alert messages. Oh, by the way, we actually, I believe we're at about 500 peers that have already upgraded to 2.1. Like with any release, it usually is like a long tail where like the first 24 hours of a release coming out, there's like this like initial spike because there's people who are using the auto upgrade script, and then it like rolls out and extends for a long period of time, and then we hit another upgrade and it does that same spiking pattern again. But right now that we're about 500 for a network that had a very, very, very long pause on frame progression, that's pretty awesome to see, especially considering that like the overall prover count on that is averaging around 20 to 30 provers a piece. So it looks like at least the initial cadre of the network is going to be eating pretty healthy on rewards. And then we also have the message queues from the messaging system that are being processed. And so very, very simple like wiring up and connecting of all these different surfaces and how they come together. And you'll see that exact same pattern followed for the app shard consensus. It's literally going to be the same series of events except the global topics it's not listening to. And so the way that this works out when you look at the structure of the various consensus engines is that you have a series of like specifically things that connect to the consensus state machine. They're all prepended with consensus underscore. So you can actually like easily visually separate those things out. Like those relate to the consensus state machine. The coverage events and event distributor, if you see event, then it relates to the event distributor which should be relatively obvious. If you see anything around message underscore, it relates to pub/sub. And so you'll also see, not just in these packages, but you'll also see in other packages a metrics.go. We added an absolute just shitload of different metrics that your machines are monitoring. And not like metrics in the, monitoring and analytics of the creepy spy way, but monitoring and analytics in terms of, I'm running a node, I need to know if my node is performing things in a proper way, if my node is healthy, if my workers are having like weird types of contention happening. We have so many Prometheus monitoring counters that you can look at for your own node. If you set it up, you have to enable it, but if you set it up, you can just export all that into Grafana and look at it and see at a very quick glance whether there's anything wrong. And then, of course, any wiring up for services, for like the actual gRPC services, we just have it all plugged in here. Easy peasy. Then we get to the prover system. This one's a little complicated, so I'm not going to like deep dive this one tonight, especially because we're already 45 minutes in. But the prover system is essentially the, when you have the global execution engine running, like now during the enrollment phase, but consistently thereafter, you are basically getting a bunch of transactions that are saying, hey, I want to be a prover. Here's my worker count, and here's the shards that I want to like lay claim to. When that enrollment process concludes and you're allocated for the actual shard, you end up inside the prover registry. And so it's this like very like efficiently cached database that tells the overall network like what you are expected to be working on and proving for. The way that this works is that it is assigned to, of course, the application shard addresses, but it's also indexed to your prover key. And you'll notice that there's a large number of keys that get created when you start up a node. So in Q 2.0, if you were accustomed to everything, like literally everything about your node, your rewards, your seniority, everything was just like intrinsically related to your pure ID, that's gone. Obviously, like if you had coins that were associated, but those are still there. But if you expect that, that's gone now. And instead, your peer ID is fully separated from your prover key. And the reason we do that is because linking your peer ID to your prover key reduces you, like your node, your prover's identity, it reduces the anonymity of your node. And so by separating that out, where your peer ID is unrelated to the actual proofs that's being produced, it gives you a greater degree of anonymity and safety. Because like, take for example, Solana, you know, their series of provers, or I guess not provers, but block producers, that's set in sequence with their proof of stake mechanism. For the longest time, node operators were constantly getting denial of service attacks because everyone knew who they were. They knew what their address was. They knew when they were next in sequence. And so it made them very easy targets for attack. So instead, we actually have that separated out. So it becomes a lot more difficult. Plus also, the entire network is, you know, in separate shards. So you would just have a lot more surface area you'd have to attack. And it would be very, very expensive to do it. Okay. Trying to fit. I think I will be able to get through. I'll talk about the reward system. I know a lot of you are curious about that. And then we'll get through the time reel. And if we have enough time, I'll dive into the actual hypergraph implementation. But if we don't, then we'll have to kick that to the next one on Sunday. So let's go ahead and talk about the reward system, since I know a lot of folks are very interested in that. And also let me check to make sure that I don't have any questions popping up. AWS connected beds before 2.1. Yeah, are we happy about that though? Oh, you meant you meant the thunder about waiting for the enrollment to finish. No, doesn't matter. Beacon's dead, man. It's done. It's over. The network is now officially decentralized. Okay, so let's talk about the rewards, because I know that a lot of people are very interested in that specifically. Of course, it's the main incentive of the network. I get it. The way that it works, if you read the Proof of Meaningful Work document that I published quite a while ago now, we talked about the overall formula of how rewards are calculated on the network. It's very simple. It's a very simple formula, and the implementation of it, like we had to use, decimal types, so it's a little bit verbose, but even that's actually pretty simple. Problem is, if you do the simple route, it's very slow. Like doing this calculation is actually really, really freaking slow. And so the way that we got around that is we obviously put in a much more optimized implementation. But we left this like non-optimized version so people can like use it for reference if they're like implementing the node in another language, or if they're just wanting a frame of reference to make sure, like say you change something about the optimized proof of meaningful work implementation, which is what the nodes are actually using. If you change that, you have something to compare it to that's a reference implementation. And we, of course, have tests. We have, if I recall correctly, these are the benchmarks. This was a long while ago when I wrote this. But these benchmarks are where you can actually like see the performance of the different implementations and determine like, which one's right for you. Because, for example, we do have another one that exists, and it's in the optimized implementation, I believe. Yeah, the minimal allocation. For really, really tight, like low amounts of memory, like say one worker on one machine, and that's all you could actually scrounge together, like that kind of like low allocation, you'd want to swap in this implementation, for example. Okay, so let's get into what that actually amounts to. When you look at the tests, you'll actually see the relationship. What the current difficulty level is essentially like how many steps of the verifiable delay function it takes before a new frame is produced. Then you see the overall state in bytes, like the world state, and that's literally like taking the hypergraph at the global level, getting the size value from that and shoving it in there as the total amount of state. And then the overall units, because one of the things that we've been talking about is this notion of alternate fee basis app shards. And if you're doing that, you might have a different denomination, you might have a different divisor for your units, and so you have to specify it. But for Quell, it's, oh God, I'm going to butcher this, aren't I? Yeah, no, it's 8 billion units per Quill. And so you plug in those values, you get an out value, and that's the reward for that given like global interval. And then that gets split out accordingly. And so you can see how that's calculated here. And then when you actually get to the overall application of that, there is a global intrinsic operation called shard update, which takes in the shard frame headers, calculates the value based on the world state, the overall shard state, and divvies it out accordingly. And you can like dive into the actual mathematics of that and how it's applied. Your checkpoint will be the materialize function under that. And yeah, okay. Let's get into the time rail. Now, I've talked about this in previous sessions, so I'm not going to talk about the motivation for why the time rail exists. But the key things that you'll want to look at, either the app or global time rails, is essentially it's the mechanism in which frames get written to the store, and it's the mechanism in which the fork choice, if you're familiar with like traditional blockchains, it's where the fork choice mechanism comes into play. And so you'll see it get called a few different times. I'm going to just look for it. Yeah, okay. So you'll see on the insert method, there's a few different places it can occur. We have the documentation like in the form of comments around like what are the conditions in which fork choice events can happen. Also, in addition, there's some that relate to whether or not you're running an archive mode or not. One of the things that's important about 2.1 is frames are essentially self-verifying. And so when you're at the point, if you were running 2.0, you might remember that we had like this really long lead time. Like if you started a node, you had to wait a really long time to sync up, or you'd have to download a snapshot so that you'd at least be close enough. That's gone. if you're not running in an archive mode node, which most people wouldn't be because there's not much of a point to unless you're running an Explorer or something, then you only hold up to 360 frames. And so that saves a lot of space, and it also means that your fork choice evaluations may snap ahead if you've had enough like evidentiary support through the proofs to snap you ahead. And so you can think of this kind of like what Vitalik's been talking about with ETH 3.0, the idea of a stateless Ethereum. We're already there, like the future's now. And so this is essentially an example of that. Like the ability for us to snap ahead without having to actually impart trust on the network is a very powerful tool. And so yeah, like I was saying, the thing you'd probably be most interested in with the time reels is the insert method, of course, but the fork choice method. And the way that we actually did fork choice was just like a lot of the other aspects of this. One, very like deeply commented, so you can actually understand at a glance what this section of code is doing. But most importantly, when it comes to how fork choice rules are applied, the actual fork choice rule itself is wholly separated out. It's its own structure, or its own method at least, that has like a structure for the parameters that you'd apply to it. Because again, there might be reasons why you'd have different applications, like different app shards with different fee basis, or you'd have different rules. We support that. But if you're just using regular Quill app shards, the default is here. And the fork choice rules are very simple. And again, as mentioned, they're very like thoroughly commented to explain some of the math that's being applied here. And of course, like with everything, just shitloads of tests. Okay, let me check real quick. Man, I am having so much trouble with Twitch right now. Okay, let me check this. Okay, cool. I won't really like deeply cover this. We have the validators, which are the like frame validators. Yeah, I'm sorry. I'm just now seeing some of these messages. Like my phone is lagging super hard on getting these messages from Twitch. But yeah, anyway, we have the frame validators. It's not crazy different logic from 2.0 on how the frames themselves are validated. The overall like request structure is different, but like in terms of like if you were previously doing a lot of data exploration for 2.0, it's kind of the same concept with one really big freaking caveat, which is the data's encrypted, so you won't be able to like scrutinize the data anymore. Let me see what else I can squeeze in here, because I need to actually, part of the reason why we're cutting this in half is if there was anything that I needed to address during this launch period. And of course there is. We have 2.103 that needs to come out, and so I'm gonna need to drop off for that. Let's see. We used to have everything inside the crypto package under the node project for like proof trees and stuff. If you were watching the development, we moved all of that into a separate package outside of the node project, so that way other things could use it. But we do have the tests here because they're wired into the like hard-coded implementations. Actually, you know what? Let me dive into that. I know this is a little scattershot. Bear with me. It's been like 6 months since I've done a stream. Let's actually talk about that real quick because that's going to be important. So the overall structure of the root of the project, there's a couple of different packages that'll matter. We have the alias package, which is related to the client. That part's, like the alias part's published, but the client part's not published yet. Bedlam, which is our circuit compiler. BLS 48581, which is our implementation of BLS 48581, the curve. And in particular, the KZG proof system. There's bulletproofs, which is what provides the transaction privacy. channel, which is our encrypted and encrypted direct and group messaging channels. That's what Quorum makes good use of. Client, of course, is the Q client. Config is our config package. Contest is just a simple connection test utility. It was used to actually diagnose the why the launch had like basically tripped over itself at the end of September. Let's see. Consensus, of course, is the state machine. Crates are the Rust implementations that we have bound to the Golang side, and that has all the different pieces that you'll see corresponding packages for here. So like Ferret, which is our oblivious transfer library, and EMP-OT and EMP-Tool, which were the C++ implementations that plug into Ferret. Let's see. Obviously, our libp2p forks, we have fully taken over our own forks because they decided to hand over ownership of those projects. The hypergraph implementation, which is the CRDT, that's also separated out. Netcryptology, which isn't used that much anymore, but that was the OG cryptography library that was originally maintained at Coinbase. I took it over when Coinbase decided to deprecate it. Internal politics are fun. But it's still used for a few things like multi-party multiplication, because there's a faster way to do it for elliptic curves, and we have an implementation for that here. Let's see. RPM is our random permutation mixnet library. And then, oh yeah, okay, so then there's types, which are essentially the interfaces and sometimes implementations of various types that are used in the node and the client. Utils, which are some common utilities. The VDF is our verifiable delay function implementation. And then Varenk, which is our verifiable encryption library that we use for the oblivious hypergraphs data store. So yeah, that's basically the structure. But all of those, like I was saying, a lot of these things were previously in the crypto package. Any of those native implementations, they were in the crypto package. Those all got moved out into their own separate things. But we do still have the tests because our integration tests have tags as integration test. And the reason is because our services, in our overall pluggable things like the execution engine, if we just had the native bindings for all of those tests, one, that could be kind of a waste because then you'd be actually testing a lot more than just that singular item. But two, you wouldn't be able to just run it through Visual Studio Code or whatever your IDE is. You would have to actually run our test script that we have in the node folder. And the reason for that is because of all those native bindings. But because instead we put anything that uses native bindings into a integration test tag, they those are all segmented out. So that way you can actually run most of the tests inside your IDE, and it's a lot more efficient. It tests only the thing we care about. Let me see. Yeah, I think we're at the point that I'm gonna have to call it for now because we're at the hour. Let me check real quick, see if there are any questions that we can handle before then. By the way, for full disclosure, for those, because a lot of y'all are in Europe. I've found Europe and Asia. It's like 3 a.m. here, so I'm a little bit scatterbrained because I've been up all day too. It's been a long couple days. Let's see if there's any additional questions. God, I swear these things are such a pain in the ass. Why is Twitter like this? Okay. Cool. So yeah, I missed a bunch of questions. Thank you, Twitter. All right. So the first one is, Cassie, I'm not a dev or coder, just someone keen to switch my web activity as a user to Quilibrium. When will I be able to do this? Yeah, okay. So one of the things that we want to roll out, it won't be part of, it's not part of this 2.1 release, but it likely won't even land in 2.2. It might. If we end up getting a good test of it going, it might, is MPC TLS. So, like I said, the way that this network works is for connections between peers. We have an onion router, and of course, it's very easy to find. Node, P2P, onion. And the onion router has presently, some checks in place to make sure that the circuits for the onion connections being made, that, like you can't accidentally or intentionally use a node as an exit relay for traffic, like an exit relay would be for Tor. One, because there's problems in public exit relays, as many people who have run one have found out. But two, that's not the purpose of this network at this moment. Like we aren't supporting that yet. So instead, right now it's just internal service traffic. But when we support the MPC TLS primitive, which might be 2.2, might be 2.3, that's what's going to enable private browsing. Essentially, you'd be able to use the network as a distributed VPN. We're not there yet. We will get there. But if that's what you're looking for, that's when. If you're talking about websites that are hosted inside the network via, the names via QName service, the actual data via the oblivious hypergraph, that's actually now. When Quorum Mobile is published, it's going to have the first public implementation of our WebKit tooling, which is essentially what enables a browser, just like it looks like any other browser, to connect to QNS domains, and that will actually be routing through the onion router of the network. Okay, I don't know if you actually had live video transcription of this that was translating this into Chinese, but holy crap, if so, that's super cool. I just saw that photo posted. Let me check Twitch real quick, because if we're at a good standstill, this would be the time to call it, because we have got 2103 to go roll out, because I think it just got done with signing. Let me check. Okay, we're almost there. All right. I don't see any other questions on Twitch yet, but it is also kind of a pain. It sometimes takes a second to load, so I'm going to just give you guys a couple more minutes to ask any questions that you've got. Otherwise, we'll close it out. In the next stream, we're going to go through some of the more deeper components in particular, because one of the things that I want to do as part of the deep dive is I want to actually go through the process of manually constructing creating a token, transacting with a token, putting data on the hypergraph, what the actual structure of the prover entries that's currently happening for enrollment, and of course, launching applications. And so I want to walk through all these intrinsics, but that needs to be inside its own section and also not in the midst of a launch like we currently are. Okay. Hey, I assume this is the same Risky Biz from the Discord. Hello, hello. Cool. Well, you came in at the tail end. But yeah, I don't see any other questions, so I guess this will be the time to call it. Let me double check real quick. I'm gonna check the probable spam section, which is probably gonna be the messages that we should never see my reaction to on live stream, but I'm gonna do it live anyway. Oh wait, what the hell? Yogurt, why are they hurting my boy? Yogurt, why are you in the probable spam section? That's wrong. Okay. But no, I don't see anything weird. Cool. All right, so I guess we'll wrap it up here. As I said, the next stream, I already have it set up in Twitch, so you can check the calendar and put on notifications for the next stream. We'll cover the rest of the walkthrough on 2.1, and then we'll also, if time permits, we'll actually get to the point where we're doing raw development. I might, depending on how Sunday works out, I might be able to also toss in the Q console related stuff, because assuming there's no crazy hiccups, we should be able to start rolling out those services pretty quickly. So I guess that pretty much wraps it up. Cool. Like I said, thanks for bearing with me. This was a kind of like haphazard stream. It's been a while since I've done one of these. I gotta get back into the swing of things. If you have any other questions, feel free to reach out. Obviously, I'm on all the various social channels for the most part related to Quilibrium. Always happy to answer. Usually awake at times I shouldn't be, usually responsive at times I shouldn't be. So if you have questions, I'm happy to answer. All right. Thank you all for watching, and I will see you this Sunday.